All right, just some quick facts on oscillating springs. This is similar to the pendulum video. Even though a lot of this information has been shared in other videos, this is kind of collecting it all so that you can just kind of review springs by themselves all at once. So the first thing that I'm going to just talk about is some of the maximum and minimums as this oscillating spring is going back and forth. Based on what I have drawn here, I've got this is its equilibrium point, and this is like pulled all the way back. I'm not showing the all the way in point, but that's another maximum displacement. So anything that applies to this maximum displacement also applies to that one. So going back and forth, when it's let's start here. When it's pulled all the way back here, that's when it's going to have its maximum spring potential because it has its maximum displacement, which means also it's going to have its maximum spring force acting on it. So lots of maximums happening on there, and because the spring force is maximum, it's also going to have a maximum acceleration. So all of those things are maximum there, and then the corollary would be at this point here, it actually has no spring force acting on it because it has no displacement. Because it has no displacement, it has no spring force acting on it, and it has no acceleration, all at that position there. As it moves from maximum displacement inwards, it's going to be speeding up, speeding up, speeding up. And as it passes through equilibrium, that's where all of the spring potential has been turned into kinetic. So that means it's going to be moving at its fastest speed at that moment right there. So that means the minimums are right here. It would have actually no kinetic energy there and no velocity there. So make sure that you know these maximums and minimums. Lots of questions kind of are on these. They should be some of the faster questions for you to be able to answer, and some of the ones you should really feel confident about answering because they are pretty straightforward. Now, for this hanging spring, something that I want to address. So I want to remind you guys the definition of amplitude is the difference between the equilibrium position, which in the case of a hanging spring is not the natural length of the spring, but where the force of gravity and the force of the spring are equal. So this is equilibrium where mg and kx are equal, even though it's not necessarily at rest at that spot if it's been oscillating up and down. So I have the amplitudes are right there, which means over a full cycle, it's going to move a full 4 amplitudes because it's going to go all the way down and then all the way back up. So amplitude down, amplitude down, amplitude up, amplitude up. So it moves 4 amplitudes down over the time of a full period. And that's how we would figure out the average speed that the block is traveling. So keep that in mind. And let's see. I can say, what am I trying to say here? Yeah, I could definitely say that this amplitude right here, if it's released from its initial position down to here, then the amplitude x would be equal to mg over k. So we can also kind of plug that in over here and say that like the velocity would also be 4m mg over kt equals the velocity, or the total displacement that it's going to travel would be something like 2m, or sorry, the displacement from the top to bottom would be 2mg over k, or all the way from top to bottom 4mg over k. So just some kind of like math manipulation stuff that comes up every once in a while. Last thing to talk about is the period of a pendulum. Remember that it is based off of the mass. As mass increases, period increases, but not in a linear relationship. There's that square root there, so that if the mass doubled, the period would only go up by the square root of 2, but if the mass quadrupled, the period would go up by 4, and so on. It's also based off of the spring constant. So as the spring constant goes up, the period goes down. If the spring constant went up by a factor of 2, the period would go down by the square root of 2, or 1 over the square root of 2, and so on. Remember, though, the big thing here is that the displacement x doesn't change. It does not change the acceleration or the period. Oops. X would change the spring potential energy, it would change the kinetic energy that we have at the equilibrium position. But because x also increases the distance it's traveling, it doesn't make a difference in the period. So those are the big facts on oscillating springs. One thing that I do want to mention, though, with these vertical springs is that even though it is hanging vertically, G, the strength of the gravitational field, it will affect where the equilibrium point exists at, but it won't affect the period. As G increases, you can see that X would also increase, but there's no G term in here, so it has no effect on the period. It only affects where it would stay, like at rest. So that's everything, hopefully, that we need to know on oscillating springs. Thank you for watching.